Okay, so in this revision video I'm going to be having a look at permutations and combinations, as you've already seen. So I know you had a bit of trouble with this in the class, so hopefully this video will clear some things up. Before I do get started on permutations and combinations though, you're going to need to remember what factorial notation is. So when I say factorial notation, I mean, for example, 4 factorial, and the symbol that we use for factorial is this exclamation mark there. 4 factorial means 4 by 3 by 2 by 1, and it has to go down to 1. So if I'm saying to you, by the way, that would be 24. So if I'm saying to you 10 factorial, it has to be 10 by 9 by 8 by 7 by 6 by 5 by 4 by 3 by 2 and all the way down to 1. So 10 by 9 by 8 by 7 on its own would not be 10 factorial. It needs to go down to 1. So it's when we multiply a number by all of the numbers below it down as far as 1. And there is a symbol on your calculator, this exclamation key, and that will do factorial notation for you. So you don't actually have to go listen them all out one by one by one. The calculator will do that for you. So that's factorial notation. You're going to need this in this section, so I just mentioned it there first. The second thing you need to remember here is the fundamental principle of counting. And an example of that is, let's say you go into a restaurant and there are three choices, say, on the menu for starters. Let's say you have soup, you've like chicken wings or something, and then some sort of a salad. And then maybe the main course, there are just 2 options. You might have steak and you might have curry. So basically what I'm saying to you is there are 3 ways you can pick the starter, and there are 2 ways you can pick the main course. So I'm saying that there are 3 by 2, which are 6 different options I can pick. Now I'll prove that with this example, and hopefully you'll just believe it for the rest. The fundamental principle of counting says that if there are m ways of doing one thing and n ways of doing another thing, well then there are m by n ways of doing both things. So let's just see that that's true for a second. I could go in and I could get soup and steak, or I might get soup and curry. Or what about wings and steak, or wings and curry? So far that's 4 different meals I could have gotten. Or what about salad and steak, or salad and curry? So there's the 6 different options I could get. So with 3 starters and 2 main courses, it's not that hard to list them all out. But if there were 20 ways of doing one thing and 10 ways of doing another, that'll start to get confusing if I wanted to list them all out. So that's known as the fundamental principle of counting, and it's important to remember that if there are m ways of doing one thing and n ways of doing another thing, well then there are m by n ways of doing both things. So they're the 2 pieces of information you'll need to remember before we start to revise our permutations and combinations. Alright, so we're going to start with permutations. Okay, so when I say permutations, I'm really looking at the number of ways I can arrange different objects. So imagine, for example, you have a bookshelf. Now, this is not going to be a very good shelf at all, but it's just a straight line. Imagine you have a bookshelf, and let's say you have 5 different books. Book 1, book 2, book 3, book 4, and book 5. And I'm looking at each of these books, and I want to figure out how can I arrange these books on the shelf. There are 5 places on the shelf. So there are 5 sections on the shelf. Just extend that out there. So there are 5 places on the shelf, and I have 5 books. So how many books can I possibly choose to put in position number 1 on the shelf? Well, I could put this book in, I could put this book there, this one, or this one. Basically, there are 5 books that could go in that position. Now let's imagine I've used up one of these books, so that one's gone. So that means for position number 2, there are actually now only this one, this one, this one, or this one. So that's 4 books that I can choose for this place. So put that back. So we have 4 books that we can choose for position number 2. And then we have 3 books, because remember one of them is used up. Now we've 3 books used up. So there's only 2 books left for this position. And then we have the last book. So there are 5 books, 5 ways of me arranging the first ones, and then 4 ways of arranging position number 2, and then 3 ways for position number 3, and then 2, and then 1. So using the fundamental principle of counting, which we came up with before, we can tell that there are, well, 5 by 4 is 20, by 3 is 60, by 2 is 120, by 1 is 120. So there are 120 different ways that I could rearrange 5 books on the shelf. Well, look at this. This is 5 by 4 by 3 by 2 by 1. That's a really long thing to have to write out every time. So remember, our shortcut for that would be 5 factorial. So there are 5 factorial ways of rearranging 5 books on a shelf. So that's if I wanted to use all of the books. What if I only wanted to take 3 of the books? How many different ways can I rearrange them? So I have 5 books. Let's just make these books smaller this time. I'll still use squares for them. So we have 5 books. And here's our shelf. But this time, our shelf only has 3 spaces on it. So how many books can I put in position 1? Well, I can only put 1 book there, but how many books do I have to choose from? I could choose this book, or this one, or this one, or this one, or this one. I have all the books I could choose. So in fact, there's 5 different books I have the choice of putting there. Now only one of them can go there, but there's 5 I could pick to put there. And once I've put a book there, there's now only 4 books left. So that means I've 4 books I could pick from to put here. And now there's another book gone, so now I've only 3 books left to pick from. So there's 5 ways of arranging the first one, 4 ways of arranging the second one, and 3 ways of arranging the third one. Now that would not be written as 5 factorial, because remember, it has to go 5 by 4 by 3 by 2 by 1 to be a factorial. So unfortunately you'd have to do that out in your calculator or in your head, 5 by 4 by 3. Unless you use the shortcut. What about if I did just continue down to 2 by 1? So because of the fact that I've added on, well, multiplied on by 2 and then multiplied by 1, to counteract that I really should also divide by 2 by 1. Just so I haven't actually affected the sum, because the 2 and the 2 will divide into each other and the 1 will divide into each other. So the sum still is 5 by 4 by 3, but the reason this makes it a bit easier is because I can just write it as 5 factorial for the top, because now the top of the fraction does go 5 by 4 by 3 by 2 by 1, and on the bottom I can write 2 factorial. So you might be saying, sure, what's the point in doing that? 5 by 4 is 20, by 3 is 60. That's easy. Yeah, and that is easy enough, but when you're dealing with larger numbers like 100 by 99 by 98 by 97 all the way down as far as 40, and having to do all of them out, it'd be better to be able to do 100 factorial over 39 factorial. So that's why we do this. So it's 5 factorial over 2 factorial. Let's just do another one of them. I'm not finished with that example yet, because I do want to make this even more relevant to what we're doing. But I'm going to just do these for a couple of examples of this first before we go any further. So let's have a look at a question here. I'll take one from your book. So how many... No, we won't go with that one there. So we have this one here. How many in the letters of the word bridge? So we've got this word bridge, B-R-I-D-G-E. And they're asking you, how many ways can the letters be arranged in a row if you take 4 of them at a time? So basically, I only have 4 slots to fill because I'm taking 4 of them at a time. So there are 1, 2, 3, 4, 5, 6. There are 6 letters in the word. That means there are 6 letters I could choose for position number 1. And once I've used a letter, there's now only 5 letters I can choose for position 2. And then 4. And then 3. Now, to answer this sum, you would say 6 by 5, 5 6s are 30. 4 30s are 120. And 320s are 360. So your answer to this would be 6 by 5 by 4 by 3 equals 360. So there are 360 different ways I could rearrange the letters of the word bridge if I take them in fours. But again, we want a faster way of doing this, something that we can do on our calculator. And even though there are only 4 numbers there and you'll be quickly able to say 6 by 5 by 4 by 3, we want a way that will work for larger sums. So let's say, for example, we have 6 by 5 by 4 by 3. What if I continued that on and went down by 2 by 1? That makes the whole of that line 6 factorial. But I just came along and randomly done that 2 by 1, so to counteract that I'd need to also divide by 2 by 1. So I'd be dividing by 2 factorial. And if you do that out, 6 factorial over 2 factorial, we're going to get 720 over 2. And 720 over 2 is 360. So we get the same answer. But it just means instead of us going 6 by 5 by 4 by 3 and stopping, we can go 6 by 5 by 4 by 3 by 2 by 1 divided by 2 by 1. In other words, 6 factorial over 2 factorial. So what if we want a general way of looking at this? In the previous example, we had 5 factorial over 2 factorial. How did I know to stop at 2 factorial? Well, what is 2? 2 could be written as 5 minus 3, because 5 minus 3 is 2. And I'll explain why I'm doing that now in 1 second. I'll just do that with this one as well. 6 factorial over 2 factorial. Why 2 factorial here as well? Well, I could write that as 6 factorial over 6 minus 4 factorial, because what's 6 minus 4? 2. And maybe you'll notice a pattern here if I go back up to the other one. It was 5 minus 3, and remember, I had 5 objects, and I was taking them in threes, and the bottom of that fraction says 5 minus 3. In the word bridge, I had 6 objects, but I was taking them in fours, and I have 6 minus 4 as the bottom of the fraction. So basically, what we're trying to get at is a general formula that will work for any permutation. If I have n objects, and I want to take r at a time, well then the formula the formula is going to be n factorial divided by n minus r factorial. And that will tell me the number of permutations of n objects, taking r of them at a time. And we write that as NPR, and you might notice an NPR button on your calculator, and you can use that, but I'd rather if you get used to using the formula, because you will need it for much more complex sums later on. So we have NPR, the number of ways of taking permutations of n objects, taking r of them at a time. So thinking of our book example from earlier on, we had 5 books, and we wanted to take them in groups of 3. So that should be 5 factorial over 5 minus 3 factorial, which is 5 factorial over 2 factorial. So 5 factorial is 5 by 4, which is 20, by 3, which is 60, by 2, which is 120, by 1. All over 2, which tells us there are 60 different ways of rearranging the books. And if we think of the letters for the word bridge, there are 6 letters in the word bridge, and I wanted to take them in fours, so it should be 6 factorial over 6 minus 4 factorial, which is 6 factorial over 2 factorial, and that gives us 720 over 2, which is 360. So this is the exact same as what we had above. 6 factorial, 2 factorial, 6 factorial, 2 factorial, 5 factorial, 2 factorial, and so on. So the formula for working out the number of permutations of n objects, taking all of them at a time, is n factorial over n minus r factorial. So we'll have a look at combinations now. The only difference between permutations and combinations is that in a combination the order doesn't matter, whereas in a permutation it does. And what do I mean by that? Well, the best way to explain that is with an example. So let's have a look at combinations. Here's a permutation of the letters ABC. ABC is one permutation. Another permutation would be BCA. Now they're two completely different permutations. They are not equal when they're permutations. They're totally different. Alright? But ABC is equal to BCA if they're combinations. So they are the same thing. So let me just fix that. So combinations are the exact, once the letters are the same, you go to the cinema with your two friends. It doesn't matter if one's sitting on the left, one's in the middle, one's on the right. It doesn't matter where you're sitting. It's still the same three people that go to the cinema. So ABC, BCA, they're still the same three letters. It doesn't matter which way they're arranged. So they're the same combination, but they're a totally different permutation. So we're going to be talking about combinations now. So let's just think of the following. For example, we have the letters ABC, and I want to take them two at a time. So I'm going to look at, first of all, the permutations. So we know that if we're taking them as permutations, it's going to be 3 factorial, and I'm taking them two at a time, so it's going to be 3 minus 2 factorial on the bottom. So 3 permutations, 2 objects. So that's going to be 6 over 1. So there should be 6 different permutations. So let's try and list them out. We'd have AB, we'd have AC, and we'd have BC, but we'd also have BA, CA, and CB. So that's the 6 completely different permutations. So there are 6 permutations, but if you look closely, AB and BA are the same two things, AC and CA are the same two things, and BC and CB are the same two things. So if they're all the same as each other, we can effectively say ignore that, and ignore that. So while I have 6 permutations there, I actually only have 3 combinations, because it doesn't matter whether it's AB or BA. It doesn't matter who's on the left, who's on the right. They're the same two things. So AB and BA are the same two things. So 3 combinations. So we had 6 permutations. We have exactly half that many combinations. So 6 divided by 2. I have 3 combinations. So let's try and figure out a formula for working out combinations. We'll do this with a bigger example. Let's think of the letters A, B, C, D. A, B, C, D. So let's figure out how many permutations. I'm going to take them in groups of 3. So using our formula for permutations, we know that we have 4 objects, and we want to find the number of permutations when we're taking them in groups of 3. So that's going to be, remember our formula, NPR. It's n factorial over n minus r factorial. So in this case it's going to be 4 factorial over 4 minus 3 factorial. So that's just 4 factorial over 1 factorial, which is just 4 by 3 by 2 by 1, which is 24. So there are 24 different permutations of the letters A, B, C and D when I take them in groups of 3. So let's write out them. We'll actually write out the full 24 of them. Now I know you might think this is a bit time consuming, but hopefully I will really explain the idea to you. So we'll start with, we could have A, B and C. We could have A, C and D. Or what about B, C and D? Or D, A, B? I could have A, C, B. I could have A, D, C. I could have B, D, C. And D, B, A. So I'll just fill these in as fast as I've written them out here in front of me, because there's no way I'll be able to think of them on the go like that. So DAC, CDB, ADB. So we're trying to write out all 24 of these permutations: BCA, CAB, CBA. Then we're going to have DCA, CAD, and CDA. We're going to have CBD, DCB, and DBC. And then the last three are going to be ABD, BAD, and BDA. So there are 24 permutations. I'm just going to drop a line down between each of these here. We have 24 different permutations, but if the order doesn't matter for a combination, well then technically ABC, ACB, BAC, BCA, CAB and CBA, they're all the same 3 letters. They're just rearranged differently. So really that's just one combination there. Or what about ACD, ADC, DAC? Again, these 6 are all the same. They're just rearranged differently. These 6 are all the same. Same 3 letters used each time. And these 6 are the same 3 letters used each time. So in actual fact, because they're all the same letters used each time, I can totally ignore all of them ones and say that there are actually only 4 combinations when I have 4 letters and I want to take them in groups of 3. There are only 4 combinations. Now let's try and figure out a relationship between permutations and combinations. There were 24 permutations. For every single group here we have 1, 2, 3, 4, 5, 6. There are 6 different permutations in each group there. So there's 6 less combinations than there are permutations. So 24 divided by 6 gives me 4. And that's why we're left with these ones up here are 4 combinations. Because for every one of those combinations in each column there are 6 different rearrangements of the letters. ABC, ACB, BAC, BCA, CAB, CBA. They're all the same. So I don't have to look at all those 6 yellow lists there. I just have to look at one of them. So for each of those lists, there are 6 times less than there actually are. So even though there are 24 permutations, there are 6 times less combinations. So that gives us 24 divided by 6, which is 4. If we go back up here, we had 6 permutations, but there were 2 times less combinations because every permutation was doubled up. So how do we figure out a formula for working these out? Well, that's 6 there. How do we know that there's going to be 6 of each one of them? Well, we know that there are 3 letters, A, B and C. How many different ways can I rearrange those 3 letters? Well, there are 3 letters I can put in position 1, there are 2 letters I can put in position 2, and there's 1 letter I can put in position 3. So I should have known already that out of these letters A, B, C here, there were 6 different ways I was going to be able to rearrange them. These letters A, C, D, there are 6 different ways I can rearrange them. There are 6 different ways I can rearrange them. There are 6 different ways I can rearrange them. So that's why I'm dividing by 6, or better yet, 3 factorial. So it's 24 not 24 factorial, sorry, it's 24 divided by 3 factorial instead of 24 divided by 6. So if I have 4 items and I want to take them, number of combinations when I take them in groups of 3, well, it's going to be the same as the number of permutations. So permutations was n factorial over n minus r factorial. So it'll be the same as the number of permutations, because that's the 24. But I'm also going to be dividing by, in this case, 3 factorial, but it's only 3 factorial because I'm taking them in groups of 3. So that means I'm also going to be dividing by r factorial. So in this case I'm dividing 24 divided by 3 factorial. 24 was the number of permutations. So that's this bit of the formula. But I'm also then dividing by the number of ways I can rearrange the 3 objects. So that's that bit of the formula. So if I have 8 objects and I want to find the number of combinations when I take them in groups of 4, I could say that that's 8 factorial over 8 minus 4 factorial. That will give me the number of permutations. But I also need to divide that then by the number of ways I can rearrange those 4 objects. So I'd also be doing divided by 4 factorial. So I know that this is confusing enough stuff, but you just think of the logic behind it, okay? And I know that there's an awful lot of marker and that going on up here, and you're probably a bit confused by what's really going on. So just think about it one more time. We're looking at these 24 different permutations there. But really, this one here and this one here, these are all the same. So while there's 24 permutations, I don't have to include, like, they're all the same as each other as well. So I only have to count them once. I only have to count them once. I only count them once because they are all the same. So instead of counting the full 24, I actually only have to count 1 from each column. So that's why I'm saying there's 4 combinations. So the first thing we do is we figure out how many permutations that there are. So that's, remember, n factorial over n minus r factorial. So we figure out how many permutations that there are. And in this case I divide it by 6, and I'm dividing by 6 because there were 6 different rearrangements here. So how would I figure out how many different rearrangements there are? Well, because there are 3 objects, there must be 3 factorial arrangements of them. 3 by 2 by 1, and that's where the 6 comes from. So that's why in our formula we also divide by r factorial, or the number of objects that we have. So that's our formula for the number of combinations. So a quick reminder, if I have a permutation, order is important. If I have combinations, order is not important. So I hope that helps with permutations and combinations. I'm sure if you have any questions, ask me in the class.